Okay, hello class. We are now in chapter 2 of journal 1.5. So we're talking now about the title is how to compute exact areas with something called an antiderivative. And hopefully that word suggests antiderivative is the opposite of a derivative. And so here's our definition. And then antiderivative is also often called an integral. So to compute these rather than differentiation rules, we'll have integration rules or anti-differentiation rules. Those mean the same thing. But it's easy to see that by the definition of the word, antiderivative, anti-differentiation, that we are like undoing differentiation. So you want to make sure when you're doing a problem where you need derivatives, you're in one mindset, and then you kind of got to switch over when you're doing a problem that needs antiderivatives or integrals. Okay, so f of x is an antiderivative for a function, little f of x, so make sure you see the distinction there between capitalization and lowercase. So function little f has an antiderivative if the derivative of the antiderivative is the function. So again, antiderivative, derivative, those two things next to each other, we're going to see that those are inverse operations. One does something, the other one does it, and then you would get the function back. So let's just work a few examples. Again, we're sort of in the first couple pages of chapter 2. So the type of tests that you've seen before are derivative exams. Here's a function, take a derivative. Here's a function, take a derivative. Now we're going to do the opposite. Here's a function, find the antiderivative. Here's a function, find the antiderivative. So kind of working backwards. And what we have on the board is the next page. We have this box with a definition of an antiderivative. That's our definition right here. We're going to start with. And the example, the very first antiderivative we want to try to compute is just, let's just take this nice power function x cubed. What is the antiderivative of x cubed? So I need a function that when I take its derivative gives me x cubed. So you think about that for a moment, pause the video and give it some time. And probably you'll come upon something like this. Maybe you'll try that the antiderivative is capital F, that's our notation. Maybe you'll try like x to the fourth. And then for that to be correct, to be an antiderivative, it has to be that you took the derivative of that. So the derivative of capital F is times the power down a power, just nice power functions. That's not quite x cubed, that's 4 times. It's 4 times too many. So one thing we could do is, what if we try taking that x to the fourth and just multiplying by a quarter? Will that get us there? So now we take it times the power down a power. When we take the derivative, we get 1/4 times 4, so we get x cubed. Right. That's correct then. This is an antiderivative because by the definition of antiderivative, the derivative of the antiderivative is the function back, x cubed. Okay, so we're going to be doing this. You're going to sort of be cranking away with some computations on getting good at, I give you a function, you tell me the antiderivative. I give you a different function, you tell me the antiderivative. And the reason we want to do this is we're actually going to connect it back to stuff we did in chapter 1. In chapter 1, we were getting approximate areas, but we want to ultimately get exact areas. And the key concept is that's going to be connected to antiderivatives. So in the beginning, you just want to get good at given a function, find the antiderivative. And then a couple more videos will explain, once you're good at getting antiderivatives, how you take that antiderivative and somehow turn it into an exact area. So it's a preview of where we're going. This is our first problem where we did an antiderivative. But a few more things we have to note is that this isn't the only antiderivative that would work. Here's another one that might work. 1/4 x to the fourth plus 7. Is that an antiderivative for x cubed? If it is, it has to be that I take the derivative of capital F, the antiderivative, and I get x cubed. Does that work? Okay, the first part is a power rule, yeah. The second part is a constant, derivative of a constant is 0. So yeah, that worked. Okay, so I could say 1/4 x to the fourth plus 7 is also an antiderivative of x cubed, but so is, 11. That's also a function that when I take its derivative, I get x cubed. So is 15. So is minus 15, right? The derivative of any constant, whether it's positive or negative, is 0. So in general, what we often say is to just cover all those possibilities. We say 1/4 x to the 4th plus c, where c is what is called your constant of integration. So any constant will do. The next thing to note about this, find the antiderivative of x cubed. I've stated that question in English, but I could have also compactly give you the exact same problem with this new notation. This little squiggly is like an elongated S, and actually from the Latin, Newton and Leibniz, actually it was Leibniz who gave it this name. S, it looks like an elongated stretched S for summa in Latin, which is sum. So eventually we're going to be able to relate this to those Riemann sums that we did in chapter 1. Okay, so this is a notation that just stands for the integral sign or the antiderivative. Really, this means the exact same thing as this statement. It really says find the antiderivative of x cubed. This little dx means with respect to x. If we were in Calc 3, there might be other variables, but for us, almost always x's. So not too much is happening with this dx for us in business calculus. So we want to find the antiderivative of x cubed. We did that a couple ways. It is 1/4 x to the 4th plus c. Okay, so again, this was the integral sign. This tells you with respect to x. And if you would complete this, your answer would be 1/4 x to the 4th plus c. If you actually do the integration, you remove the integration sign, your answer is then a function, which is a capital F that represents an antiderivative. Okay, now we're going to move on to some integration rules that we're going to learn. There are many integration rules. Just like for derivatives, there's many differentiation rules. For a particular function, you apply a particular rule. So if you have a very complicated function, you have e's and ln's and sines and trigs and those sorts of things, you would apply e's and ln's and sines and cosines rules. But we're going to focus on polynomials in business calculus. So these are the few rules that we need. So we're going to focus on these 3 rules of integration, which are also anti-differentiation rules. And again, the beginning of this chapter, we want to get good at doing those. And then we'll see later in the chapter that we are doing all those calculations so that we can get good at computing exact areas. Okay, so I'll leave those rules up and then we'll work a few problems where we're going to practice using these rules. I'm going to pull some problems from the end of the chapter that we'll take a look at. Okay, these are the typical type of problems you're going to see in this chapter, where it's really saying find the antiderivative of 4 with respect to x, find the antiderivative of this function, x cubed plus x squared with respect to x, find the antiderivative of 1 plus 2x minus 3x squared. All of these are nice polynomial functions, again, the kind that we see often in business calculus. And so to find the antiderivative, you could do what we did on the previous example, sort of like think about it and work backwards. And maybe we'll try that on a few of these, but sometimes it's going to get a little tougher to sort of work backwards, and there's more efficient ways because we actually have these rules here. So the integral of 4, so I need a function that when I take its derivative, I get 4. Again, pause the video, think on that for a moment, and hopefully you'll come up with 4x plus c, right? That's working backwards. Just thinking about it for a moment, what's a function when I take its derivative, I get 4? Okay, well, it had to be linear, 4x, but don't forget to add the constant of integration because it could have been 4x plus 7, 4x plus 11, 4x plus 15, 4x minus 2, 4x plus pi. Right, so any constant would work, and we've done the integration, we removed the integration sign. You can always check your work when you do an integration problem. This also could have been written with these instructions. Find the antiderivative of f of x equals 4x, right? That's the exact same instructions as it's shown compactly here. You can always check your work by taking your answer, taking its derivative, do you get the original function back? I'm sorry, oops, the original problem was just 4. Okay, so we did that by just sort of thinking about it, working backwards, but that's actually the constant rule. So if you want to integrate some constant k with respect to x, you get kx plus c. That's really what we just used there. Now the second example, we're actually going to use a couple rules. We're going to use this power rule and the sum rule. Sum works for sum and difference. It could be plus or minus. We're going to just think about it first time with the sum rule. Okay, so it turns out that the sum rule helps us say, well, there's really two parts here. There's stuff before a plus sign and stuff after a plus sign. And I can really think about this as two separate integrals. The integral of x cubed with respect to x plus the integral of x squared with respect to x. When I treat it that way by the sum and difference rule, I really divide it into two smaller problems. So I'm really wondering, is there a function, capital F, that when I take its derivative, I get x cubed? So again, you could try to work backwards. That's what we started this video lesson with. That was 1/4 x to the 4th. And I could do the same thing over here. What's a function that when I take its derivative, I get x squared? I might try x cubed, but that's a little bit too big because I'd have 3 times x squared when I take the derivative. So it's actually going to be 1/3 x cubed. And then plus c, you can think about adding 2 plus c's, but there's really just, either way, that's just a constant. So we just add 1 plus c at the end of all that. So I worked backwards to do that, but there's also, I could have done it directly from what's called a power rule for integration. The power rule for integration should remind you of the power rule for differentiation in the sense that they are inverse operations. The power rule for differentiation, remember you go times the power down a power. Well, the power rule for integration, you do the opposite of that, which is up a power over the power. Okay, so that phrase should help you. If you have x raised to the n power and you want to take the antiderivative to integrate it, you take that thing up a power. So we go x to the 4th, we add 1, divided by the power. So that's where the times 1/4 comes in. Same thing for the next integral we want to do. We want to take it, it is a power rule, it's x raised to some power, we take it up a power over the power. So that's x cubed divided by 3, which is the same as 1/3 times x cubed. Okay, so this second example, we got to use the sum rule and the power rule. And now the difference rule would say, instead of pluses, if you have two things that are subtracted, you can divide that into two integrals that are subtracted. Right? So in general, we just say plus or minus. That covers both the sum rule and the difference rule. So let's do that on this third example here. If I want to integrate this, I get to use all 3 rules. And let's write them all out. We can think of this as the sum rule, which is the integral of 1 with respect to x, plus the integral of 2x with respect to x, minus the integral of 3x squared with respect to x. So we use the sum rule, a difference rule, and then when we integrate this, we'll need a constant rule, a power rule, and a power rule. So I'm going to have something plus something minus something plus c. So it's the structure. We'll take them one at a time. The first part, I need to integrate 1. That's a constant. The constant rule says you just do 1 times x, so x. You can always check, is the derivative of x 1? Yes. So you can always check your integration by applying a derivative. Okay, the second one, I need to integrate 2x. Well, it doesn't quite look like it fits the power rule, but remember, x is raised to the invisible 1 power. So now I can take that x up a power, so that's x squared divided by 2, but don't forget to multiply by the 2 that's sitting there. So this is really 2 times x squared divided by 2. These 2's would cancel out. Right, now a similar rule is going to apply when you're multiplying by a constant, just like for differentiation, that constant gets carried along when it's multiplied by it. So I'm really asking myself for a moment, I know I'm going to have the 3, I know I have the minus sign. So I'm really just saying, what is the antiderivative of x squared? I need a function. And then when I take its derivative, I get x squared. It fits the power rule. So the power rule for integration, we take it up a power over the power, so it'll be x cubed divided by 3. The 3's go away, so I'll have x plus x squared minus x cubed plus c. That, down here at the bottom, is our final answer. This is the antiderivative of the original function here in the red box. It's a function that when I take its derivative, and you can always check, take the derivative along this line, do you get 1 plus 2x minus 3x squared? Yes. Okay, I'm going to erase the board and put a few more up here. Okay, let's look at these 3 additional problems. And first thing, just like with derivatives, for this first one, square root of x, it doesn't look like it fits one of the rules we have. We don't have a rule that involves square roots. But just like we did with derivatives, when you see square roots, turn them into their exponent form. So this is the same thing as x to the 1/2 dx. Sorry, here's the culprit. She'll try to behave. Okay, so we were working on this problem where we mentioned that because there's a square root, we turn it into an exponent form. And now it does fit the power rule. It's x raised to some power, just like the power rule for differentiation. It's okay that that's a fraction or a decimal or negative. We can still do the power rule for integration. And so we take it up a power over the power. So you add 1 to the exponent, so that becomes 3/2, or if you like turn it into decimals, that's 1.5. So x to the 1.5 divided by 1.5 plus c. Or if you like fractions, x to the 3/2 divided by 3/2 is the same as multiplying by 2/3 plus c. I mean the same thing. Check your work by taking the derivative of the antiderivative, and you should get square root of x back. Okay, the next one also fits the power rule, but the reason I put this here is just sometimes the variable is not always x. It might be t's or p's or y's. And so here we're going to do the same thing. We're going to integrate with respect to y, and we will get y to the 5/3 divided by 5/3 is the same as multiplying by 3/5 plus c. Again, if the fraction is a problem for you, just change it right from the beginning to its decimal form, 0.66. Okay, and then the last one here on the board, we want to integrate this. We see we're going to use the sum and the difference rule. We see we'll use the constant rule. We know this is x to the invisible 1, so we can do a power rule on that one. It's this first one that we don't have a rule that has a fraction, and it has to be able that we can massage this to fit one of these rules. And so the massaging that goes on for this 5 over x cubed is that's the same thing as 5 times x to the minus 3, right? So it crosses the bar and becomes a negative exponent then, or vice versa. When you go up or down, you're just changing the sign on that. Now it does fit the power rule. We can take it up a power over the power, but make sure when you add 1 to -3, you get -2. So on the next line, we're doing the integration, so we don't need the integral sign anymore. And we know 5, it'll be 5 times the antiderivative x to the -3. That's up a power x to the -2 divided by -2. The next one is a power function, up a power over the power, x squared over 2. We add x squared over 2. The last one is a constant rule, and so we subtract 3x plus the constant of integration. This is the antiderivative. You could leave it like this, or you can clean it up. For some problems, it might make sense that you wanted to write -5/2. That's, you can write as a fraction or a decimal. Divided by x squared, so if you wanted to bring that x to the -2 down, plus 1/2 x squared minus 3x plus c. Always, 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 with integrals, you can check your work by taking the derivative of this, and you get the integrand back. Okay, so quick summary. A couple topics, we learned some vocabulary. Antiderivative is a function that when I take its derivative, I get the original function back. Don't forget the constant of integration, because they actually create a family of antiderivatives. And then some notation, this integral sign is like an elongated S. It's somehow going to relate to those Riemann sums of chapter 1. That'll be next videos. When we practice, we're going to practice taking antiderivatives, or also known as integrals, of several types of functions. The functions we're going to deal with are polynomials, because we see those most often in business calculus. So we'll have the power rule, the sum and difference rule, the constant rule. So the main ones you need to know. There's several pages in the beginning of chapter 2 where you practice on different functions using these rules.